Alright, so in this video we're going to be talking about waves in a closed pipe. And whenever I'm talking about a wave in a closed pipe, what I mean is one end of the pipe is closed and the other end of the pipe is open. And we're going to talk about how waves resonate naturally in pipes with one end closed. So what the fundamental frequency, or the first harmonic, looks like for a wave that is inside of a closed pipe. So the fundamental frequency, the wave, would look something like this right here, where this area where the two lines, the solid line and the dotted line, where those two lines are really far apart from each other, that's an area of high pressure. Whenever they're close, that's an area of low pressure, because we know that sound waves move as pressure waves, where there's areas of high and low pressure. So for the fundamental frequency, you have this high pressure area here and this low pressure area here, and that creates the first harmonic. Now if you look at that, and we'll come over here and we'll draw a wave just for reference. So a wave looks like this. Okay, so this is what a complete wave looks like. This ends up only being a quarter of a wave. So the length of the pipe is actually equal to 1/4 of a wavelength. So it would be wavelength over 4. So this section right here is only reminiscent of just a quarter of a wave. So it's just from equilibrium to this part right here. So that's what it looks like whenever you have the fundamental frequency, or the first harmonic, of a closed pipe. And you see that the length of the pipe is equal to a quarter of the wavelength. So what would the second harmonic be? Well, we'll draw a pipe. We'll assume it's the same length. The second harmonic would have two fundamental frequencies crammed into this pipe. So what you would have is you would have a quarter wave right here, and then you would have another quarter wave right here, because we did the first quarter of a wave and then we did the second quarter of a wave. So we would kind of reflect it down here like this, where the pipe ends up going right here. Now, what you end up having here is half of a wave, because 2 quarter waves equals a half wave. So the length of the tube would equal to half of a wave, or the wavelength over 2. Now, something interesting happens on the second harmonic whenever you have a wave going through a closed pipe, and this generates no sound, okay? So some people don't even really consider this a harmonic because it doesn't resonate at this point. But this is what the second harmonic would look like in a pipe closed at one end. But because you have this area of low pressure and low pressure, there's no sound resonating out at the second harmonic. So, like I said, some people don't even really consider that a harmonic. But if we were to go up to the third harmonic, we'll do this, where we go like that. Now we're going to put 3 fundamental frequencies, so 3 quarter waves in here. So we'll do 1 quarter, a second quarter, and then a third quarter down here. And then we'll reflect that like so. And what you have here is you have 3/4 of a wave. So the length of the tube is equal to 3 lambda over 4. So it ends up being 3/4 of a wave. Here you do have sound, so that's good. And let's go down here to the fourth harmonic. Draw that one really quick. We're going to put 4/4 of a wave inside of our pipe. So we'll have 1 quarter, 2 quarters, 3 quarters, 4 quarters, and we're going to reflect that like so. And what you notice is the length of the pipe, well, 4/4 ends up making the whole wave. You got the up and then down, it comes back. Looks like a whole wave like this. So the length of the pipe ends up equaling, well, a wavelength. But once again, the fourth harmonic has this area of low pressure right here, and there's going to be no sound resonating out. So once again, this will be no sound. All right. So a couple little things to know. The fundamental frequency. So we'll write these facts over here. Fundamental frequency, or the first harmonic, is only a quarter of a wave. So the length is whoops, got a little lag going on there. All right, so the length of the pipe, it only can hold a quarter of a wave. All right, so that's the fundamental frequency. Also, another thing that we need to consider, whatever this frequency is, the second harmonic is 2 times the fundamental frequency. The third harmonic is 3 times that frequency. The fourth harmonic is 4 times that frequency, and so on and so on. The fourth harmonic, the fifth harmonic, the sixth harmonic. You can just keep following this process. Another thing to notice, only odd harmonics resonate. Only odd harmonics resonate. And this is only true for closed pipes. So only the odd harmonic, or the odd, only the odd harmonics are going to resonate. So the first, the third, the fifth, the seventh, the ninth, the 11th, only those harmonics are going to actually create a resonating sound. Even harmonics, no resonance. So we'll do that. We'll write that down here. Even harmonics do not resonate. Resonate. There we go. All right, so that's how you can figure out how waves and resonance works in pipes closed off at one end.